Good morning, students. In today's lecture, we will discuss the endomorphism rings of a module. So first of all, we discuss the notations used. Let us take M and N are two modules over the ring R. Then the set of all the R homomorphisms of module M into the module N, that is denoted by the symbol home. In the bracket we have M comma N, and in the base we have used the suffix R. So this is the notation for the set of all the R homomorphisms of module M into the module N. In particular, if M and N are same, in that case this will become the set of all the endomorphisms of module M, and it is denoted by the symbol endomorphisms of M. So we can write end, in the bracket we have M, and in the base we use the suffix R. So this is the notation, or you can use the notation home, in the bracket M comma M, and in the base you can write R. So this is the notation for the set of all the endomorphisms of module M. Now we will discuss the endomorphism rings in detail. So our next theorem is M is a left R module. Then we will prove that the set of all the endomorphisms of module M, that is a ring with unity. So let us take M is left R module. We already discussed in the examples of modules that every additive abelian group is a Z module. Now because M is left R module, so it is additive abelian group. So we can say that M is a Z module. Now let us denote the set of all the endomorphisms of M over Z by the notation W. Now we are to prove that this W is a ring with unity. So first of all, we show that W is non-empty. This W is the set of all the endomorphisms of the Z module M, and module is additive abelian group. So we can say that W is the set of all the endomorphisms of additive abelian groups. Now to show that W is non-empty, we will show that the zero homomorphism of modules M belongs to W. So let us define a zero mapping from module M into itself by taking an arbitrary element M. The image of M under this mapping we have defined by zero element of M. Now we can easily show that this mapping is a homomorphism of abelian groups, because if we take two elements M1 and M2 belonging to M, then the image of M1 plus M2 under this mapping, that is 0, and which can further be written as the image of M1 under the 0 mapping plus image of M2 under the 0 mapping. Means this mapping is a homomorphism of abelian groups. So by definition that will belong to W. So we can say that W is non-empty. Now next we define addition in W. So let us take F and G, two elements belonging to W. So by definition of W, F and G are homomorphisms from M into M of the abelian groups. Now we define the addition of F and G as follows. So let us take an arbitrary element X belonging to M. Now because F is a mapping from M into M, so image of X under F, that will be an element of M, and also image of X under G, that also belongs to M, and M is additive abelian group. So F of X plus G of X, that belongs to M. So we can define the mapping f plus g as image of x under f plus g is equal to f of x plus g of x. Here x belongs to M. In this way, we have defined the addition of two elements f and g belonging to W. Now we claim that this W is a ring with unity. So first of all, we will have to verify the 5 conditions of abelian group under addition: closure, associative, identity, inverse, commutative. So first of all, we show the property, closure property under addition. Let us take two elements M1 and M2 belonging to M. Let us find the image of M1 plus M2 under F plus G. Now by definition, this can be written as, by using this definition, this will become f of M1 plus M2 plus g of M1 plus M2. Now because f and g are elements of W, so they are homomorphisms of abelian groups. So image of M1 plus M2 under F, that will be image of M1 plus image of M2. And also under G, that will be image of M1 plus image of M2. Now we can write this as f of M1 plus g of M1 plus f of M2 plus g of M2. And this can further be written as image of M1 under F plus G. And this can be written as image of M2 under F plus G. So we have proved F plus G belongs to W. So this proves closure property under addition. Now next we show associative property under addition. So let us take 3 elements F, G and H belonging to W. Now we are to prove that F plus G added to H will be same as F plus G plus H. So let us start from the left side by taking an arbitrary element M belonging to M. Let us find the image of M under F plus G plus H. Now this is one of the mappings and this is another mapping. So by definition of addition, which we defined already, this can be written as image of F under F plus G plus image of M under H. This can further be written as image of M under F plus image of M under G plus image of M under H. Now we can combine these two. So we can write this further as f of M plus G plus H of M. And this can further be written as F plus G plus H of M. So we have proved the associative property with respect to addition. Now next we prove the existence of additive identity. So let us take an arbitrary element F belonging to W and let us take M belonging to M. Now let us find F plus 0 mapping and image of M under this mapping. Now again this can be written as f of M plus image of M under the 0 mapping. So that will be again f of M. And similarly we can find the image of M under 0 mapping plus F. And we can see that this is again f of M. So by definition we have proved 0 mapping plus F is same as F, or F added to 0 mapping again gives F. So by definition we can say that this 0 mapping, that is identity element of W. Now next we prove the existence of additive inverse. Let us take an arbitrary element F belonging to W and we define its additive inverse. So let us define the mapping minus F from M into N by taking an arbitrary element M and its image under minus F we have defined as negative of F of M. And you can easily verify that this mapping is a homomorphism of M into itself. So we can say that this mapping minus F belongs to W. Now we are to prove that F added to this mapping minus F, that gives us the zero homomorphism. To prove this, let us take an arbitrary element M belonging to M, and we find the image of M under the mapping F plus negative of F. By definition of addition, we can write it as image of M under F plus image of M under minus F. So these will be cancelled out, so we get 0. So image of every element of M under this mapping is 0. So we can say that this mapping is zero homomorphism. And similarly you can find minus F plus F, that will also be zero mapping. So by definition we can say that minus F is additive inverse of F. Next we verify the commutative property under addition. So let us take two elements F and G belonging to W and an arbitrary element M belonging to M. Let us find the image of M under F plus G. Again, by definition of addition, this can be written as F of M plus G of M. And this can further be written as G of M plus F of M. And this can further be written as image of M under the mapping G plus F. So we have proved F plus G is same as G plus F. So till yet we have proved that W is an abelian group under addition. Now let us define the multiplication in W. To define the multiplication, let us take F and G belonging to W, and we define mapping FG from M into M by image of M under the mapping FG is equal to F of G of M. Here this M belongs to M. Now let us verify the properties: closure property, associative property, distributive property. Now let us verify the closure property with respect to this multiplication. So let us take two elements M1 and M2 belonging to M. Now let us find the image of M1 plus M2 under the mapping FG. By definition of this mapping, this can be written as F of G of M1 plus M2. Now because G is an endomorphism from M into itself, so this can further be written as G of M1 plus G of M2. Again, F is an element of W, so that is an endomorphism from M into itself. So this can further be written as image of G of M1 under F plus image of G of M2 under F. So we have proved image of M1 plus M2 under the mapping FG is equal to image of M1 plus image of M2 under the mapping FG. This proves that the mapping FG belongs to W. Now next we prove associative property with respect to multiplication. So let us take three elements F, G and H belonging to W and an arbitrary element M belonging to M. Now we are to prove that Fg into H is equal to F into GH. So let us find the image of M under Fg into H. Now by definition of the multiplication which we defined already, this can be written as Fg of H of M, and this can further be written as F of GH of M. So we have proved Fg into H is equal to F into GH. So this proves associative property with respect to multiplication. Now our next property is distributive property. So let us take three elements F, G and H belonging to W and an arbitrary element M belonging to M. Let us find the image of M under F plus G into H. Now by definition of multiplication in W, this can be written as F plus G of H of M. Now this can further be written as F of H of M plus G of H of M. Again by definition of multiplication, this can be written as image of M under the mapping FH plus image of M under the mapping GH. And this is true for every element M belonging to M. So we can say that F plus G into H is equal to FH plus GH. So this proves right distributive property. Similarly, you can prove the left distributive property. So we have verified all the conditions of the ring. So we can say that the set of all the endomorphisms of M, that is a ring. Now it remains to prove that it is a ring with unity. Unity means multiplicative identity. So let us define a mapping I from module M into itself by taking an arbitrary element M from the module M, and we define its image under the mapping I as M. This mapping I, that is a endomorphism of module M, because if we take two arbitrary elements M1 and M2 belonging to M, then the image of M1 plus M2 under I, by this definition, that will be M1 plus M2. Now from here, M1 is I of M1 and M2 is I of M2. So this proves that I is an endomorphism of module M. Now we have to prove that this I is multiplicative identity. So let us take an arbitrary element M belonging to the module M and F belonging to W. Let us find the image of M under F into I. By definition of multiplication in W, this can be written as F of I of M. I of M is M, so this will become image of M under F. And again, if we find the image of M under the mapping IF, this can be written as I of F of M. Again, by definition of I, image of F of M under I will be same as F of M. So this proves that F into I is equal to F, and from here I into F is equal to F. So by definition, we can say that this I is the multiplicative identity. So we have proved the set of all the endomorphisms of M, that is a ring with unity. Now in the next theorem, we will prove that the set of all the homomorphisms are homomorphisms of module M into itself, that is a ring with unity. Now to prove this, if we have a mapping M from M into M, which is a homomorphism of modules, then by definition of homomorphism of modules, two conditions are satisfied. First condition, for two elements M1 and M2 belonging to M, image of M1 plus M2 is equal to image of M1 plus image of M2. And for R belonging to ring R, image of Rm is equal to R into image of M. This M is the element of module M. Now, because F is endomorphism of abelian groups, and therefore we can say that F belongs to the ring of endomorphisms of M over the ring of integers. So we can say that the set of all the homomorphisms over the ring R, that is contained in the ring of the homomorphisms over Z. So we can see that this is subset of this ring, and therefore if we can show that this is a subring of this ring, then this will become a ring. So to prove this is a ring, we will prove that this ring is a subring of ring of homomorphisms of module M over Z. So first of all, we prove that this is non-empty. The set of all the homomorphisms from M to M over the ring R is non-empty. For this, we will prove that the zero mapping belongs to this set. So let us define zero mapping from M into M by taking an arbitrary element from here. We have taken M belonging to M and we have defined its image under this mapping to be 0. Now you can easily verify that this is a homomorphism of R modules. Now let us take two elements M1, F1 and F2 belonging to the set of R homomorphisms of module M. Now to prove subring, we will have to prove that F1 minus F2 and F1 into F2 belongs to this set. So first of all, we will prove F1 minus F2 is a homomorphism, R homomorphism of module M. So let us verify the conditions for homomorphism of modules. First condition, let us take two elements M1 and M2 belonging to M and we find the image of M1 plus M2 under the mapping F1 minus F2. Now this can further be written as image of M1 plus M2 under F1 minus the image of M1 plus M2 under F2. Now because F1 and F2, these are belonging to the set of R homomorphisms of module M, and therefore by definition of homomorphism, this can be written as image of M1 under F1 plus image of M2 under F1, and this can also be written in the same way, and we can combine these two terms. This will give us image of M1 under F1 minus F2, and this gives us the image of M2 under F1 minus F2. So our first condition for module homomorphisms is satisfied. In the second condition, let us take R belonging to the ring R and M belonging to M, and we find the image of Rm under the mapping F1 minus F2. Now this can further be written as image of Rm under F1 minus image of Rm under F2. Again, because F1 and F2 are endomorphisms of left R modules, so by definition this can be written as R into image of M under F1, and this can be written as R into image of M under F2, and this can further be written as R into image of M under F1 minus F2. So till yet we have proved F1 minus F2 belongs to the set of all the homomorphisms of module M over the ring R. Now to prove F1 into F2 belongs to the set of homomorphisms of module M. So let us find the image of M1 plus M2 under the mapping F1 into F2. By definition of the mapping F1 into F2, this can be written as F1 of F2 of M1 plus M2. Now by definition, because this is endomorphism of modules, so this can be written as F2 of M1 plus F2 of M2. Now again, this can further be written as F1 of F2 of M1 plus F1 of F2 of M2. So this proves our first property of homomorphism of modules. In the second property, let us take a scalar R from the ring and M belonging to module M. Let us find the image of Rm under the mapping F1 into F2. Now by definition of this mapping, This can be written as F1 of F2 of Rm. F2 is homomorphism of R modules. So image of Rm under F2, that will be R into F2 of M. Now again, F1 is also an endomorphism of left R modules. So we can write it as R into F1 of F2 of M. So this proves that F1 into F2 that belongs to the set of homomorphisms of module M. So both conditions for subring are satisfied, and hence we can say that the set of all the homomorphisms of module M into itself over the ring R, this becomes a ring. Now our last step, we are to prove that this is a ring with unity. So let us define mapping I from M into M by image of M is equal to M, where M is an arbitrary element of module M. And you can easily verify that this I is a homomorphism, R homomorphism of module M. Now we are to verify that for F belonging to the ring of homomorphisms of module M, F into I is equal to I into F is equal to F. To prove this, let us take M belonging to module M and let us find the image of M under the mapping F into I. Now by definition of F into I, this can be written as F of I of M. I of M is M. So image of M under the mapping Fi is equal to image of M under the mapping F. And this is true for every element M belonging to M. So this proves that F into I is equal to F. In the same way, you can prove I into F is equal to F. So by definition, we can say that I is unity element of this ring. So we have proved the set of all the R homomorphisms of module M into itself, that is a ring with unity.